This is the second lecture in our study of cell structure, and we previously talked about the central role of cells in the organization of the human body, that cells are where life exists, um, that levels of organization below this are not alive, but all the rest of the living structure of the body is based on cell structure. When we got to the third um, When we got to the third statement in the cell theory, it talked about all cells come from previous cells. And when we talk about the cellular nature of our human body, the question, of course, comes up, how many cells? How many cells are there in the human body? Are there hundreds and thousands, millions, billions, or trillions? These numbers get very, very big, and they're almost unbelievable. Um, if you equate this to money, of course, some people have salaries and in the millions. Um, some people um, in the financial industry or in the computer industry have billions of dollars. Nobody has trillions of dollars. But this is one of the few ways to think about how big these numbers are. Um, so in the human body, how many cells are? Well, they're numbered in the trillions. And just how much is a trillion is a very, very complicated, but a very, very unbelievable number. And you and I are not even 1 trillion. The average human body is somewhere in the neighborhood of 70 to 100 trillion. Well, the number trillion looks like this. It's actually 1 million times 1 million, right? Multiply two numbers with 6 zeros in them and you get one number with 12 zeros. The national debt is measured in trillions of dollars, and it's way more than 11 right now. Every year this class is taught, that number gets bigger and bigger. And when you say the national debt, some of you don't even know what that means, but you know what debt is. If you have borrowed money for an automobile or for a house or to go to school, or maybe you just have a credit card and you owe some money. Well, the national debt is speaking about the national government. Actually, all of the taxes that you and I pay every year don't pay for all that goes on in the government. The government borrows money on a credit card, in a sense, just like you do, and they owe somewhere in the neighborhood, I think today it's $17 trillion. It's an unbelievable amount of debt. We still don't know what that number means, though. I just said a moment ago, the human body contains about 70 to 100 trillion cells. They must be incredibly small to fit them all into this package. No wonder we couldn't see them but for a microscope. Um, Other odd things, bacteria are 10 times smaller than human cells, and you have about 10 times that number in your human body. So this number is amazing, and it's hard to get your mind around. What I think we can get our mind around at least a little bit is the concept of a million. So if you think about how much is a million and try and think of it in terms of dollars and money, if we start here, we can grow ourselves up to just 1 trillion. So if we begin with this concept and we say to you, how much to you is $1 million? I don't think any of us see ourselves as having $1 million all at once. If you earned $50,000 a year, in 20 years, you would have earned a total of $1 million. But that would be 20 years. there are game shows. This one was on a number of years ago, um, where you could win $1 million if you could answer enough questions right. Um, if you think of that, 20 years perhaps, um, to earn $1 million, but you would have spent it over 20 years too. So I want to use a spending illustration here just for a moment. Obviously, there isn't a lot of content here, but I want to use a spending illustration. And I'm hoping that you can get into this a little bit emotionally so that you really have a sense or a feel for how big a number this is. Um, so if we're going to spend 1 million, we have to have more than 1 million. So let's start off with $1 billion. Let's see if we can get our mind around how much a billion is. Um, one of the people in the United States that most people know of is Bill Gates, who um, started Microsoft Computer Systems. And he has, because he has most of or a good deal of the stock in that company, he has like $50 billion. So you've got to have more money than 1 million. But what if you could spend $1 million? What if you were given $1 million and instead of spending it out over 20 years, you had to spend that in one day? Well, most of us think, yeah, we could buy a great big house and a nice car, and it's not worth as much today as it was years ago. There was a comedy back in the 1980s when $1 million was even more than this, um, that illustrated somebody trying to spend a lot of money. This movie was called Brewster's Millions. Um, and the basic premise of the movie was this homeless man was located by a lawyer who said, "You've got a very rich uncle who's left you his inheritance, but it comes with a catch. You've got to prove that you know how to spend and use money." And so the basic idea was he could have the entire $300 million of inheritance if he could spend out $30 million in a month, in 30 days. And the catch was that to spend that money out, he had to spend it in such a way that he had nothing left after 30 days. The $30 million had to be gone. So you couldn't spend it on, say, an automobile or a house, because now you own the automobile or the house, and it's worth however many million or however many thousand you've spent for it. So you can't have any more money than before you started. So what do you spend money on where you've got nothing left after you've spent it? And so that was the trick, him trying to figure out how he could do this. And if you think about that in your own life, what could you spend money on that you have nothing left after you're done? And of course, food would be one of those things. You eat the food is gone, you spent the money. But you probably can't buy and eat $30 million worth of food in 30 days. The other catch in the story was you couldn't give it away, and you couldn't gamble it away. You had to legitimately spend it. So you could probably spend it on some big fancy meals, but probably not that much. You could spend it on travel, right? At the end of a trip or a cruise or whatever you would take, all you have is memories. The money is gone. You can spend it on parties, right? After the party's over, you've got memories, but nothing much else. So anyway, it was a comedy based on him trying to figure out how to do this so that he can inherit the full amount. So we want to do something like this, but we want to start with a bigger number because we want to get to 1 trillion. So let's start with 1 billion. Let's see what it would take to spend $1 billion, and we want to spend it at the rate of $1 million each and every single day. Now that's a lot. You could, we don't have to be Brewster's Millions. You could wind up with a lot of houses, a lot of real estate, a lot of cars, whatever. But if your task was that you were given every morning that you wake up, there was $1 million in your bank account, and it had to be gone by the end of the day, okay, there'd be quite a bit of work in spending $1 billion. How long would it take? Well, if we put the numbers up here and say how much is a billion, here's $1 million a day, and this is what a billion looks like. We'll line it all up, and maybe you can see. We're asking how many $1 million there are in a billion. And if you look at all the zeros, cancel out all the ones they have in common, and you'd wind up, if you cancel out 6 zeros in both, you wind up with 1 in the $1 million category and 1,000 in the $1 billion category. So essentially 1,000 days, right, of spending, right? $1 million each and every day for 1,000 days would be $1 billion. And look at that. It would take you 3 years to do that. If you had $1 billion in the bank account and you spent $1 million today and $1 million tomorrow, it wouldn't be gone for 3 years. What will you be doing in 3 years? It's approximately 3 years. But you get the idea. That's an enormous amount of money, right? Spending each and every day for 3 years of your life. So you can see, I think, now that $1 billion, and Bill Gates has $50 billion, and there are other investor people that have that much money. You couldn't spend it in a lifetime, could you? Right? If you had 50 billion and it took you 3 years to spend one, it would be 150 years to spend that out at the rate of $1 million a day. So this is an enormous number. Now, the kicker is that if we go up to $1 trillion now, let's try to spend $1 trillion at $1 million per day. How long would that take? And actually, this number is even more crazy. Nobody has $1 trillion to loan us. The government does. So if we could borrow $1 trillion from the government, I guess. But let's put the numbers up again. How much is $1 trillion? Okay, so $1 trillion is 1,000 times bigger than $1 billion, right? The commas and the zeros you can see, there's 1,000 times more. So $1,000 billion is $1 trillion. So if it took 3 years to spend $1 billion, and this is 1,000 times bigger, do you get it? This is just an unbelievable number. 3,000 years of spending at $1 million each and every single day. If you started spending now, you've got 3,000 years to go. Or if you look at the way we set our dates, we're in the year 2017 right at the moment, as I'm lecturing this. But if you started at the year 0, you've spent for 2,000 years and more, and you've still got 1,000 years to go. That's just an incredible, incredible number. I hope you can see that. And your human body then is composed of trillions and trillions of living cells. You know, if we say 70 to 100, and we base that sort of on size, because cells are all the same size. A taller person, a bigger person doesn't have bigger cells. So a taller or bigger person has more cells, right, than a smaller person. So an elephant has more cells than a mouse. They have about the same size cells, but one has more than the other. So how do you get to this number? This number is so unbelievable. Think about it in terms of time, right? How many seconds would it take to count to these numbers? And of course, some of these are impossible. How long, if you counted one per second, if you counted for a day, there are 86,400 seconds in a single day, right? So if you tried to count to 1,000,000, how long would that take you? Well, it would take you about 11 and a half days if you're going 1, 2, 3, 4, and could count to that. If you were counting to 1,000,000,000 seconds, that's 31 years worth of time. And so a trillion, 1,000 times that, you know, an obvious impossibility, not even conceivable, right, that somebody could count to the number 1 trillion. So how do you ever get to these kinds of numbers? You can't, if you were counting, adding 1 second each time you counted, we certainly couldn't do that with cells. We couldn't have a human body that adds a cell every second even and get to trillions and trillions of cells. Can't even get to 1 trillion. Takes you 31,000 years. So how do you start with a single cell and get to all the cells in the human body? Because you know this, at one point in your life, you were just a single cell. That's all there was of you. A sperm cell from your father and an egg cell from your mother united into a single cell. And that cell, that one single cell, grew to you. How could that happen? Where do these cells come from? Right? You can't count to 1 trillion, right? So how do you get these cells? You can't do it by counting, by adding. Okay, and the answer is that cells increase by dividing into 2. One cell divides into 2 cells. They start and they grow larger, and when they're large enough to form 2 new cells, one cell has a mechanism whereby it can divide into 2 cells. That process is called mitosis. And only by multiplying, by each and every cell dividing into 2 cells or doubling itself, can you get to there. It's a little bit like a good illustration of this, how it can grow, is what is known as the penny experiment. It's a 30-day experiment, and the person chooses one of 2 things. It's a 30-day experiment. The first day you get a penny. The second day you get 2 pennies, doubled. You take the 2 pennies and double it, so on the third day you have 4 pennies. You double that again, and so each and every day you double the penny. So would you rather have that, or for 30 days, would you like somebody to give you $1,000 each and every day? Well, that one's easy to figure out, right? If you were given $1,000 each day for 30 days, you'd have $30,000. Could the penny doubled come anywhere close to that? It sure doesn't seem like it. Doubling pennies seems like all you're going to have at the end of 30 days is a lot of pennies. It goes like this. After the first week, on day 7, actually after day 7, you earn $1.28. That's how much you're given on the 7th day. On day 14, the penny is doubled to $81.92. Still way below $30,000. You're getting close when you get to week 3. At the end of week 3, the gift is $10,485.76. And if you look at a chart that then takes that from day 21, 22 on to day 30, it's kind of amazing because on the 30th day, the penny has doubled to $5 million, way more than the 30,000 that's there. So the numbers here, once you get to large numbers and those large numbers double, the numbers get larger and larger. If you went beyond day 30, you'd have 10 million, then 20 million, then 40 million, 60 million, 40 million, 80 million, then 160 million, then 300. So you can see after about another week, you're almost to billions. So when the numbers are small, they fool you. But when the numbers are big, they get bigger exponentially. It's a little bit like compound interest. A lot of people don't save money because they think, oh, or invest money because you don't have much to show for it. And it takes years and years and years. But if you do it faithfully with a little tiny bit of money, after 20 or 30 years, that money can grow to an enormous amount. So I guess you can see here, this is how you get to a human body with trillions of cells in it. The doubling activity of individual cells after a certain amount of time adds up to trillions and trillions of cells. So there is one other question here then. I can see how cells, when they double, are alike, right? If you start with all cells and they're doing mitosis, they come out the same, don't they? The question then is, how are different cells produced? In our first lecture in this cell structure unit, or this cell structure topic, we started by looking at 8 different cells. They weren't all alike. In the beginning, as cells first divide, they do all look alike. Early cells like that are called stem cells, and you might have heard of these on the news or in literature or whatever. Stem cells are cells that are early in human development. They're all alike. They are what we say undifferentiated. They haven't become different yet. So cells early on in the multiplication process are all like that. As the cells multiply and multiply, though, they begin to gain different environments. If you have a ball of cells, if you've got cells that multiply and multiply, some may be on the inside, some may be on the outside of this ball, and those that are exposed to an outside environment may grow differently than those on the inside. So it really is environmental influences or triggers that cause certain parts of the cell to grow differently. One of those stages of growth is called a blastula, and this picture shows you a single fertilized egg cell multiplying into 8 cells. When it multiplies beyond that, it finally multiplies into so many cells that the cells on the inside are different than the outside. The inside cells begin to hollow out, and now there's an internal environment and an external environment, and so cells begin to become very, very different. And those simple differences in the beginning produce different cells. Cells have an influence on one another then, and so these differences just cascade into major differences, and ultimately cells then become the ones they need to be in various parts of the body. And that's what you have. And so you wind up with this whole variety of cells. 70 trillion cells on average. How many different types does this grow into? Well, probably not as many as you might guess. We just spent a lot of time trying to get our head around a trillion, just 1 trillion. But the different types of cells, there's only a little over 200 different types of cells. And different scientists, different researchers disagree on this. I've seen numbers from 210 all the way up to 220, but it's still in that low 200 number. So if there's only a couple hundred different types of cells, well, there must be hundreds of billions. There must be an enormous amount of any one single cell, like skin cells. So there's going to be hundreds of billions of skin cells. All of the larger organs in your body are going to have huge numbers of cells. But only And, fix that in your mind. There's only about 210 different ones. I showed you 8 of those 210 in the last lecture. So now I hope you have a feel for the numbers and how we get to the numbers and the different kinds of cells that there are. Let's summarize for a moment. Remember, over the last 2 lectures, we've talked about cell theory, that our human body is a society of different kinds of cells. We now know there's something like 200 different kinds of cells. Every process of my human body is a cellular process, right? These cells increase by this dividing process that is known as mitosis, and then cells differentiate while they multiply. While they're growing into massive numbers, they differentiate into these different kinds of cells. And that's where we wind up with a human body, right? We've got cells growing and growing and growing. In our next lecture, what we want to do then is look in more detail at the structure of cells. And so we're going to begin to look at the organelles that make up the cells. And ultimately, we want to work into, well, what are these organelles doing? Because just like various cells have a role to play in the human body, each and every organelle is going to have a role to play in the life of a single cell. And so over the next 3 lectures, we're going to try to figure out exactly how the cell is structured and how it functions on the basis of these organelle structures. Okay, so you'll hear me again in the 3rd lecture of this cellular topic.